Welcome to the IEEE Computer Society DVP SIP virtual conference on hot topics in cybersecurity. The second day, this session is on advancements in information security algorithms. I'm Jan Bielohoubek, one of the co-chairs of this conference, and I will be the moderator of this session. The conference is brought to you by the Distinguished Visitors Program and the Student and Young Professionals Activities Committee. The Student and Young Professionals Activities Committee was developed to support the Computer Society's student and young professionals globally through initiatives targeted at advancing their knowledge, development, and careers. The Distinguished Visitors Program was initiated in 1971 by Dr. Stephen Yao and offers top quality speakers to professional and student chapters. Before we get started, I would like to get a couple of housekeeping tasks out of the way. You can ask your questions in the Q&A panel. Dr. Sousa and Dr. Jet will answer as many questions as they can following the presentation. The session is being recorded, and the slides and recording will be made available after the session. Allow me now to welcome our speakers. The first speaker is Dr. Sousa. He received his PhD in electrical and computer engineering from the Instituto Superior Técnico Universidade de Lisboa in Portugal in 1996, where he is currently a full professor. He is also a senior researcher with the R&D Instituto de Engenharia de Sistemas e Computadores. His research interests include VLC architectures, computer architectures, parallel computing, computer arithmetic, and signal processing systems. He has contributed to more than 200 papers in journals and international conferences, for which he got several awards, such as DACIP 13 Best Paper Award, SAMOS 11 Best Paper Award, DACIP 10 Best Paper Award, and the Honorable Mention Award UTL Santander Tota for the quality of the publications in 29. He has contributed to the organization of several international conferences, namely as program chair and as general and topic chair, and he has given keynotes in some of them. He has edited 4 special issues of international journals, and he is currently senior editor of the IEEE JETCAS, associate editor of the IEEE Transactions on Computers, IEEE Access, and Springer JR EIT. He is fellow of the EIT and distinguished scientist of ACM. Welcome, Dr. Sousa. You have a word.
Okay, so thank you very much for the nice and long introduction. So can you hear me well?
Yes, I can hear you.
Okay, thank you. So I will talk today in this session on advancing in information security. I will talk about modular arithmetic, and in particular residual number systems that support cryptography and security as a whole. So I'm part of DVP for the last 2 years. I'm very proud of it. So let's start my presentation. So first of all, I introduce a bit myself. So I'm as the moderator said before, I'm from University of Lisbon. So the Faculty of Engineering, which is called IST. So we have around 10,000 students, and the university 55,000 students in Lisbon is the biggest one in Portugal. And I'm also a researcher in the Embedded Electronic Systems research area at INESCAD, which is a research institute affiliated with the university. So let me give a bit of motivation. So if you think about blockchain, so I will not I will not go through the link to YouTube, but public key cryptography is an essential component, part of the Bitcoin's protocol that ensure the integrity of messages created. So it's quite important, and it's one of the main topics that I will focus today or in my presentation today. On the other hand, you have big data, high-performance computing devices, and very complex algorithms and data structure, like for instance, for deep neural network. And this is together is also related, so it's a transversal type of technology and computing, and is also important for cryptography. So I will focus a bit on the arithmetic that I will talk to you today is important also for this type of computation. So let's talk a bit about the traditional computer arithmetic. If you think of binary systems, that the position of a digit in a number corresponds to a certain height. And we have a big problem about the carry chains that make this type of arithmetic slower and difficult to implement in an efficient way. So the idea is, like you have in this picture in the bottom of this slide. So if you are able to spread the computation over different channels and make the computation in parallel, for sure, you will achieve fast computation, and you have other important characteristics or features, like, for instance, is more reliable, this type of computation, and also you can control part of the computation instead of computing in a row all the digits of a number that is represented in the traditional number systems. So this type of computation is called, this type of representation is called, and arithmetic is called residual number systems and modular arithmetic. I will introduce this type of representation in arithmetic. Then I will go through the public key cryptography main algorithms, and I will show you how we can use this non-conventional arithmetic, RNS, just to implement them. I go briefly through neural networks and that impacts on big data, and then talk a bit about implementation and design automation, present you ongoing research projects that we have, and at the end I will draw some conclusions. So if you think about residual number systems, is a quite old type of representation supported, or is not quite old representation, is a representation supported on a quite old theorem that we call the Chinese residuals theorem, CRT. And if you want to represent a number, you can, first of all, define a set of relatively prime numbers, or moduli, that we call the moduli set. So these, each component or element of this set is a relative prime when you compare with the other members of the set. And you define a dynamic range with this set that is the product of the moduli, which means that you are able to represent, if you think only on integer and positive numbers, you are able to represent numbers between 0 and capital M in this slide, capital M minus 1, which is the product of the moduli. And you can represent an integer by the remainder of the integer division of the number by each one of the moduli. And these give you the residuals, and these residuals represent, we can prove by the CRT that represent without any doubt only an integer in this dynamic range. So if you want to apply arithmetic operations like addition, subtraction, and multiplication, you can do it in parallel in each one of the residue, but you have to apply modular arithmetic, which means that you have to reduce the result again to what we call a ring, and this ring is defined by each moduli as the maximum number that you that you can represent in this ring. And like that, you can compute or make the computation in parallel, and you can control the width of each one of the moduli. You can have a large moduli set with each element smaller, or you can reduce the number of moduli in the set by enlarging each one of the moduli, and at the end you have the same dynamic range. So what is the overhead that you have, or the disadvantage that you have? So you have, in the real world, you use the binary system. So you have to convert from the binary to the residual number system domain when you start computing. And at the end, you have to do the reverse transformation between the residual number system domain and, again, the binary domain. Moreover, if you want to apply more complex operation, like, for instance, division, comparison, overflow detection, is harder to implement directly on the residual number system domain because it's an intermoduli operation that you have to combine the values of the different residues just to apply the operations. So this is a figure what you can do if you do this simple addition, multiplication, and subtraction. So you can do in parallel in each one of the residues. And we call usually to each one of these components a channel which has the residue and the modular arithmetic that is associated with this residue. So let's start describing or introducing the main algorithms of public key cryptography. So let's just go briefly. If you have symmetrical encryption, so for cipher and decipher, you use exactly the same key. When you do public, and this type of algorithms, that's why I'm not going to focus here, and we don't use this type of arithmetic because the type of algorithms that we apply are quite relatively simple in terms of arithmetic. So you can do it with logic, bitwise logic, and simple arithmetic operations. But if you go to public key encryption algorithms, which are asymmetrical, you have a private key for cipher and a private. It depends on what you are doing, but you have a private and a public key, and you use different keys for cipher and deciphering. You use much more complex mathematical operations, and these algorithms are computationally intensive. So you have several examples. For instance, RSA, you have ECC, elliptic curves cryptography, you have AlGamal, and you can do encryption and decryption, but you can also apply it for digital, to just provide digital signatures. In this case, is identical to public key encryption algorithms, but you sign digitally some data, and then you can be sure that this data has been signed by a private, let's say, a private key, if you consider it like a public encryption scheme or algorithm. So we have quite well known digital signature, like, for instance, the DSA. We have also the ECDSA, which is the DSA using elliptic curve. So I'm not going too much in detail, but this is fundamental for blockchain. So Bitcoin's protocol, for instance, used the ECDSA for digital signatures. So it is important also because you use the public key with hash functions to create an address that is used by Bitcoin users to send and receive funds. But moreover, it's quite important with the private key just to provide a signature that you given the message, and the private key you sign it, and with the public key you can verify if this data or message was signed by a particular sender. So this means that this type of cryptography is important, for instance, and you use it quite often in blockchain and Bitcoins. So let's start with a very simple public key cryptography or cryptographic protocol. So if you think on RSA, in this case, so you have a public key and you have a private key. You have Alice and Bob. It's the traditional example. So you Alice provide to Bob the public key. And if Bob wants to send a message to Alice, you just encrypt the message using the public key. And only Alice is able to decrypt the message by applying the private key. So if you look to the RSA algorithm, and I start by that because it's the simplest that you can have in terms of public key cryptography. What you do is you do exponentiation, but with reduction. So if you look to the encryption, it's just you have the message, you have an exponent, and then you do the encryption by doing a reduction mod n. And if you have the decryption, you do exactly the same, but with an exponent, which is this d that you have on the slides. And this n, you have thousands of bits. So typically nowadays, to have security, you have 4K bits. So it's a very large number. So what you do typically in sequential computation is that, so you see the bits of this d, which is the exponent for the decryption, for instance, that I have the example on the bottom of this slide. And then you go digit by digit, and sequentially you compute the square recursively. And if the corresponding digit is 0, you multiply by 1. If the corresponding digit is 1, you multiply by c, which corresponds to the cryptogram. And you do it sequentially. And this is the typical algorithm that you have. So let's see what we do in practical terms. So this n that you have here is a very large number. It's not a power of 2 for sure. So it has particular properties that I'm not going to enter in detail here. But it's important to just to respect them to have security in this type of cryptography. And then what we do for the calculation is that we apply what we call the Montgomery multiplication with reduction. So to do that, we just transpose or map a number x into the Montgomery domain by multiplying by a certain number m, which is now, let's say, the domain that I'm going to use. And then I'm going to reduce it by mod n, with n is the real number that I want to use on the reduction. So if I want to multiply in the Montgomery domain the number x by a number y, I just multiply in the Montgomery domain, which is represented by this capital M in subscript. And then what I do is that I have to multiply the result w by the reverse of n minus 1 and compute it mod capital M, which is my new number for reduction. And then I compute this zeta that is in the last line of equations in this slide by adding to the w, which is the result of the product, by the variable q that I computed before, multiply by n and divide by n. And like this, I obtain what is the x by y multiplied by m, which is reduced automatically mod m. So let's justify a bit. I'm not going too much in detail in math, but when you calculate q and you are subtracting or adding this q, but if you see you have the minus signal, what you are doing is in this numerator, you assure that is a multiple of the denominator m. So it will give you the exact result, which is an integer. And this integer, since you divide by m, you have the result of the product of x by y multiplied by m, which means that, and not the square of m, because you divide by m, which means that you have the results in the Montgomery domain. Again, you can say, oh, but this is a lot of computation. That's true, but if you think that this m is now a power of 2, so the computation of mod and division by m is just shifting to the left and to the right. Okay, so it's quite convenient, And it's the kind of arithmetic that we use on binary systems when you compute the RSA algorithm. So this is a problem if you want to use it in residual number system, because this m is not anymore a power of 2. It becomes the product of the moduli of my set. Moreover, it's not possible to compute the zeta dividing by m, because I'm only able to represent numbers between 0 and m minus 1. So what we do in terms of arithmetic when you use residual number systems is to have two bases, and not a single, or two moduli sets that we call bases, and not a single one. And then we put the variables that we want to multiply in both bases. Then we compute this key in basis, this q in basis 1. Then we convert by using the CRT to basis 2 this q, just to do the computation that I'm not able to perform on basis 1. Then I convert back to basis 1, and I provide the results in basis 2. So I have the results that I can put again at the inputs, and then apply again the Montgomery algorithm on the residual number systems domain. So if you look now to the example of RSA, but computed on with RNS, so you have the cryptogram here that you transpose to the Montgomery domain by multiplying by M1, which is the basis 1, or the moduli set 1. Then you just compute the message, which means that is result that you are going to decrypt by multiplying initial is 1, so you multiply by M1. And do the reduction by n, and then you iterate for all the k digits of your exponent that you use for decrypt, and then you apply the Montgomery multiplication. So you multiply m by m, which gives you the square that you had before, and then if the digit of the exponent is 1, you have to multiply by the cryptogram. But now the advantage is that you are doing these multiplications in the Montgomery domain using residues that can be quite small. So, and you do it in parallel. So you apply the algorithm that I presented in the last slide. So you iterate over k digits, but inside the loop, you are doing parallel computation. And at the end, just once, you have to come back again to the binary domain to have the cryptogram, to have the message m decrypted, but you do it only once. And don't forget that we are using something like 4k bits as the exponent, as I said before. So the overhead of the reversing again to the binary domain, the representation is quite small. So if you look to ECC, and I will give some experimental results of using residual number system arithmetic. If you look to ECC, what you have is that your cryptography now is performed on curves that are defined over a finite fields again. This is the typical polynomial curve that you have for cryptography. If you are using A and B, so it is too fast, but okay, let me just come back again. Oh, if you are giving, it gives C. If you are doing A plus C, it gives D, and A plus D gives A. So you are moving, adding on this finite field curve using finite field arithmetic. You can do it also multiplication, point multiplication, which is adding the point, in this case, in this example that I have in this slide, S times. So let's move forward. So the protocol is similar to the RSA. You have the public key, and the private key is a little bit more complex, the computation. But the keys, and that's why we use elliptic curve cryptography, are smaller. So which means that you use a significantly less number of bits, which is quite important, for instance, for embedded systems that you have to compute with a low budget of energy. So in elliptic curve cryptography, mainly what you do is you do point addition you do point doubling or point multiplication. So you have defined field, so you have reduction on the bottom of that. And in this the last row, what you have is finite field operations parallelization by using, again, residual number systems, because you are doing modular multiplication and addition. So you are doing exactly as we have done with the RSA. But now with a different protocol, but the arithmetic is modular arithmetic, so I can apply, again, residual number system. So I have some results for elliptic curve point multiplication in GPUs by using CUDA. This is an example that this type of arithmetic can be used to design and implement very efficient hardware, but also on software implementations of cryptographic algorithms. So in this case, the GPUs provide us massively parallelism that we can exploit. And the type of parallelism that we can exploit is mainly data parallelism. So it fits quite well what we have in residual number systems, because we have to apply exactly the same operation for the different channel or residues. And let me say that in this case, we are using 512 residues in this example, which means that my model set as 512 models, so I expose a lot of parallelism. Then I can fill and use and take advantage of all the hardware that I have in my GPU. So if you look, this is the latency in milliseconds, and this is the throughput in multiplications per second. I'm doing point multiplication. And if you look to the table, you can say that we have an order of magnitude improvement in terms of latency. So we have in RNS based around 30 milliseconds. And with the other algorithms, state-of-the-art algorithms, we need 300 milliseconds. And if you go to all through the algorithms, even for the faster one, in very old hardware GPUs, we have improvements also in terms of throughput. And if you go to the more recent GPUs, you have a speed up of 3 times. This means that we are able to use RNS to, let me just say something about this. So we have some works, and it is also quite important. RNS does not provide only improvement of performance, but allow you also to prevent attacks in cryptography, because you can change the model in your model set dynamically, and it's quite important just to prevent, for instance, dynamic or attacks that you can get in these algorithms, that someone is trying to identify the key, for instance, by tracing the power consumption and energy consumption and doing attacks. So we have some papers that show that this type of arithmetic is also provides also advantage regarding security of the algorithms of the cryptography. So let's move a bit to post-quantum cryptography. So I have talked about public key cryptographic algorithms, but the traditional ones, so RSA and ECC. So let's talk about lattice-based cryptography, which are quantum resistant. So which means that if we have quantum computers available, I can use this type of cryptography, and it is proved that it gives us security, or provide security. So what is a lattice? Once again, I'm not going in detail to the math. I give only the basic notions to show you what is the arithmetic behind that support this type of cryptography, and how we can use also residual number systems for post-quantum cryptography. So a lattice is a repeated arrangement of points. So it's a regular structure. If you have a matrix R, in this case, it's a two-dimensional space. So this R is defined by these two vectors that is represented. And then it defines a basis. And if you consider the linear combinations of the vectors that you can define by this lattice or this basis, you define the lattice. I put it here a two-dimensional example, but typically we have 200, 400 different dimensions in this type of cryptography. So what what do you use just to do encryption, we can consider in a very heuristic perspective that doing encryption in this type of lattice-based cryptography is just to have a perturbation P, which corresponds to the message, to a lattice point. So in this case, the lattice is defined by vector h0 and h1, and then I define this point h0 minus h1, and then my message is this P. I add P to this point in the lattice point, and I get the cryptogram. And we call it a bad lattice base because the vectors, the basis vectors h0 and h1 are far from being orthogonal. And this is what we can call the public key. So on the other side, on the private key, you can have a good basis, which is, in this case, is R0 and R1, which is almost orthogonal. And the decryption corresponds to finding the closed lattice vector, which in this case is R0 minus R1. And then what you do is that from the closest vector point, you will subtract the cryptogram, and you will get the message decrypted, okay? So this is a very simple perspective. So I'm going to talk about what we call bypass round of algorithm, that we change this basis by multiplying by the inverse of R, which is the basis, and then rounding the components that you have in the middle, and I map again back to the canonical basis. So we use a special case of closest vector point, which is called bounded distance decoding problem. And the bypass round off gives the closest vector for a rotating near orthogonal basis R for a lattice. So going to the math behind, so we have to compute this vector U, which is the closest integer of the cryptogram multiplied by the inverse matrix of the matrix R and multiplied by R. So I can just approximate this computation by computing the floor of the addition of this value plus 0.5, which correspond in the most right part of this equation to multiply by the determinant in the numerator and denominator, which for giving integer number for the division by 2 multiplied by d, we have to perform this reduction here by 2d. So, but to perform the multiplication with reduction, we have the Montgomery algorithm that we have seen before. So we have applied that for the computation, and the result is here in this table, also for GPUs, but not only for GPUs, but also for CPUs. And you see the dimension is started here from 400 and goes to 800, 1000 dimensions. So it's a quite huge dimension for our lattice. So we have results for the sequential version. In this case, is the number of you have the number of clock cycles, because the speed of the different devices from CPUs and GPUs. So the frequency, the operating frequencies are different frequencies. So we use the number of clock cycles just to be more fair with the comparison. And you see in parentheses what is the speed up. The speed up is not impressive, but for instance, if you see the CPU with 4 cores using AVX2 multimedia extension, which means that the speed up that we could achieve, the optimal one is 16, we are able to achieve a speed up of 11. This is the good news, that we are able also to speed up post-quantum computing or post-quantum cryptography, and not only the more traditional public key cryptography. The not so good news is that when you increase the dimension, the number of dimensions that you are using for computation, our speed up decreases. And this is due to the fact that not all the computation are performed in RNS, which means that the overhead for the other parts become more important, and therefore, at the end, we have a speed up which is less than for n equal to 400. So let's say that we applied also, and we will see at the end when I will show briefly some tools that we have to design cryptographic systems in hardware. We applied also for hardware. We have results for FPGAs. We use also RNS to implement cryptographic algorithms with reversible logic that allow you to consume less energy, because it's the type of logic that you can get also the inputs from the outputs and not only the outputs from the inputs. So we apply this type of arithmetic also in emergent technologies. But in this case, I would like to give you an additional application of residual number systems. You have more than that, but I will apply residual number system, or I will show you how to apply to convolutional neural networks. So I choose an example which is a quite well-known type of CNNs, which is the YOLO. In this case, the version 2. So what you can do is you have a CNN for object detection that is one shot. That you do both classification and bounding block estimation for a grid that you define. So you do 2D convolutional operation that fits quite well with the residual number system because it's multiplication and addition. But you do also pooling, and you implement fully connected neural networks, which means that you have to linearize some of the functions, like, for instance, pooling, that you compute the max, but it's not difficult to do so, and you can apply it with residual. You can apply also residual number systems. So in this case of the FPGA, you have it here, so you can, the computation, for instance, for the computation of the convolutions are, in this case, are represented by multiplications by the coefficients, and you have a tree of feathers. And with residual number systems, you can have a set of subtrees which width are lower, and like this, you increase the performance. So I'm not going too much in details, but you can use what you call nested residual number systems, which means that you can apply more than one level of the composition of the residuals. If I have time, I would give you more details on that. But what I can say is that if you implement it, and we have experimental results for FPGAs, you can just map or transpose from the binary to the residual number systems. You can do it in 2 levels. And like this, you have homogeneous width in your residuals. Then you can apply all the operations that you have to apply for compute the CNNs. And then at the end, you do just once the reverse conversion. So this is the CNN that we applied for giving you the results. You have convolutions, you have max pool, you have, again, some other convolutions, and you have the classification with full connected neural networks. This is the hardware that we used. So you have the slides just to see after the presentation. I'm not going too much in detail. So for the nested residual number system, we have used 2 levels, 9-bit fixed precision, we have used these synthesis tools from Vivado. So at the end, if you compare the implementation with a GPU, what you have is in terms of frames per second, you have roughly one divided by 6 in terms of the frames that you are able to process per second, but the power consumption is much lower. So if you see the efficiency is 3 times with this type of RNS representation, computing the convolution or in FPGA in comparison with the GPUs. So I'd like to say that we have some automatic tools to do the implementation of the systems, and in particular for cryptography with residual number systems. So what we do is that we define a processor with a word length of 2 multiplied by L bits by choosing a model of the form 2 power L minus a constant, which is as shorter as possible. So which means that the moduli or the modulo is as closer as possible to the power of 2, which allow us to have this congruence that you have here, which means that if you have a number that is zeta0 plus 2 raised to L zeta1, you have zeta0, and then you just have to add the constant by the zeta1. So what we do is that we have some abstraction that I have a processing element within a channel that compute for the 2 bases. If you remember the Montgomery algorithm in the RNS domain, we have the 2 bases, M1 and M2. This processing element can be a SIMD channel on a CPU, can be a thread on a GPU, or can be hardware element on FPGA or for an ASIC. So what we do is that we just go through LLVM environment and tool for the compiler. You can define your problem in C language, and then we just transform or rework on the LLVM intermediate representation. So we'll go to the program. You have an extension to the C language. We see exactly what model set we have to define. We pre-compute the constants, and then we generate at the backend PTX, which is the assembly or CUDA for the GPUs, or RTL, in this case VHDL, to synthesize on FPGAs or for ASIC. So this is an example. I will not go through in details, but as you see, this is the RSA algorithm. Is expressed like this. So you can overload your variables with the number of bits that you want. So you express that is an hexadecimal by this 0x, as in C. And then you do the RSA here. So you don't say anything about RNS. You just express the algorithm. You are multiplying by hem. You have a mask. And then you are computing the square. And with the mask, you see if you have to compute the cryptogram or not. And at the end, you have the message decrypted. So on this website, you can find the tool. You can express your algorithm. And then at the end, you have the description on software or on a hardware for your devices. So I will conclude briefly because I'm exhausting my time. We have now, we are running 2 projects. One is the European project. So I don't know if you are familiar what we call the trusted platform model, which is a standard for trusted hardware. What we are doing is that we are developing for more than 2 years. The project will end next year. We are extending this TPM, which was already standardized for post-quantum cryptography, and the project is called Future TPM. So we identify, design, and develop quantum-resistant cryptographic algorithms for symmetric cryptography and also asymmetric, and for privacy-protecting primitives that I didn't talk here, like DAA. So we are developing algorithms that we call LDAA. So we are implementing these new quantum-resistant primitives in hardware, software, and also for virtual platforms. And we are working closely to the Trusted Computing Group to standardize these primitives. So we are working with Huawei and IBM in this project, and also academic partners. And we try also to put there residual number systems. On the other hand, we finished a project last year that we called Punctual to Pierre Marie Curie University. Once again, we are moving from RSA and SEC primitives to quantum resistant primitives. And in this case, we are developing tools and methodologies for PKey cryptography. And thinking about digital markets, telecommunications, and Internet of Things protocols that we are slowly introducing post-quantum algorithms. So I can say to you that even if we don't have quantum computers in near future, these post-quantum algorithms become, for sure, standard because they assure improved security even in traditional systems. So let me just conclude because Kerry is warning me that I'm exhausting my time. So in conclusion, I can say that residual number systems improve performance of multiple crypto systems, not only performance, but also energy consumption and security. So we have shown that in practice it is efficient for RSA, ECC, and post-quantum, like for instance lattice-based cryptography. So RNS is also helpful. Is also helpful for AI, and in this case I've shown for CNNs. And what I think is important to you just to retain, because I think it changed a bit the paradigm of residual number system, is you can apply it for not only for hardware and specific and dedicated systems, but also for programmable systems and use it in GPUs, CPUs, SIMD programmable systems, etc., etc. So thank you very much. So for further readings, so I'm editing on the IEEE Circuits and Circuits magazine, the Circuits and Systems magazine. It will appear on the first quarter of 2021. You have a survey on non-conventional computer arithmetic. And then you have recent publications that you can go to more in detail to these topics that I have covered in my presentation. So thank you again for your attention. And if you have any question, I'm happy to answer.
Thank you, Dr. Sousa, for this theoretically dense talk. Currently, I can see two questions in our questions and answer panel, but I would like to remind you that you can still ask your questions during Dr. Sousa will answering, because we have plenty of time, I would say, for more than two questions. The first question I have is related to residual number system overhead. Is there any gold standard to state which is the base conversion time between the residual number system or to the residual number system while the normal encryption? The question is if the conversion phase is important from the timing perspective.
Okay, so you are talking about conversion phase, right? So forward and reverse converter. Okay, sorry. The answer is no, but the fact that makes this type of representation very well suited to the cryptography is that you are using very large integer numbers, either on traditional algorithms and on So can you hear me?
Yes, I can hear you.
Okay. Both of on traditional public key algorithms and on post-quantum algorithms. So since you have very large integers, this means that you have iterate or you have to compute even in programmable systems with a very with a very large multiple of times or iterative computation just to perform the overall computation. This means that you have plenty of opportunities to apply residual number system operations or operations or computation on residual number system domain before you have to convert again. And this is why is very, and you have seen in practice the speed up. Because you have a lot of computations to do on the residual number system domain, and just once in a while we have to perform the conversion. So forward and reverse conversion are not symmetric in terms of demanding. So typically forward conversion is much lighter. The reverse converter you can apply, so okay, I'm not going to enter in details, but you can apply two different approaches. One is the mixed radix conversion, which is more sequential or iterative, but the computation in each iteration is simpler. And the other one is more parallel, but you have to apply in a wide integer, which is this m that I represented before, and you apply the CRT. But as I said, if you are going to do only a single multiplication, even in the Montgomery domain with the reduction, so don't use residual number system. But it's not the case neither for AI nor for cryptography in practice. I'm talking about public key cryptography.
Okay, thank you for your answer. The next question is related to lattice-based system. What properties of the lattice-based system make it more quantum resistant than RSA?
Okay, so RSA is supported on factorization. The security of RSA is supported on factorization. And this is there are papers from the 90s, from the middle of 90s from Shore, that show that if you have a quantum computer, you are able to do factorization in polynomial time. It's not anymore. It does not grows. The complexity does not grow exponentially with the width of your key. This means that RSA is not secure anymore. So, and there is also a proof that by use lattice-based cryptography, for instance, for this problem of CVP that I told you in this presentation, there is no polynomial algorithm that can just provide you or attack your security of your lattice-based that you can call public key. Is not public key, but is similar to the public key cryptography. So this means that it is proved that lattice-based is secure for post-quantum computing or for quantum computing. It is also proved by Shore that it is not secure, or it is not does not assures it a secure approach. Not only RSA, but also ECC, which is supported by discrete logarithm problem, and it is also proved that you can solve the problem in polynomial time. So so the answer is you can be sure that RSA and ECC will not be used in the future if you have quantum computers. And lattice-based is secure. It is already proved.
Thank you for your answer. I can see any other answers except that people would like to thank you for a very nice presentation. So maybe I will utilize the time we have to ask my own question. Do you have any evidence that the RSA conversion sorry, residual number system conversion affects positively or negatively the side channel emissions of the implementation?
Yeah, we have a paper that so you are talking about side channel attacks that you don't know, theoretically, you don't know anything about the system. You only collect or register the power consumption along the time, or the energy consumption, and then you are able just to get some information, some important information about the key. And in this case, the more sensitive data is the private key. So what we have done in this work is to change dynamically from time to time the moduli, or some of the moduli of your set, and there is no impact in the conversion. The only problem is that it makes more computational demanding to do the reverse conversion when you change the moduli, because when you properly choose the moduli, you can have two different approaches. That one of the approaches to choose a moduli that is what we call friendly for conversion, which means that the formulation behind the conversion is simpler because I can simplify the math, and at the end I do it quite well. When we change dynamically the moduli, I lose some of this. We lose some of these properties. But in terms of attacks, there is no particular problem with this, because even you can change the algorithm that you do the conversion. And this you can do it without telling anything to the sender, because what you are doing is just when you just convert or decrypt for binary, for instance, you can choose MRC or you can choose CRT, and we have told that. And when you choose the algorithm, immediately the trace of the consumption change completely, because one is completely iterative, and you are doing over the moduli in a sequential way, and the other you are doing and reduce for the product of moduli in a very large integer, but everything can be done in parallel, which means that if you change also the algorithms for the conversion, you reinforce the security of the crypto system. But you can be penalized in terms of performance. That part is true.
Okay, thank you for your answer. We have a last question, but I'm not sure I can fully understand, because I can understand one term in the question. Maybe you will know. The question is, we do not know a polynomial algorithm to solve SVP, or it's proven that there is a polynomial algorithm for SVP. I don't know what SVP is, but...
CVP, so the closed vector point or problem. So it is at the moment, so you can never say never, right? That's the point. But at the moment, there is no algorithm with polynomial complexity for the closest vector problem. So, and this is why we say that it's and even if you have quantum computing, and that's the point, because quantum computing is a bit different of the type of computing that we have now. So you can, maybe I can point out this survey that will be published on the first quarter in the IEEE IEEE Circuits and Systems magazine. I have there a section on quantum computing, and you can see there that there is till now there is no algorithm. We cannot say that in the future there is some quantum computing based algorithm that can solve the problem with polynomial complexity. But at the moment, there is no algorithm, and that's why we say that is quantum resistant, and this is the basis for the security of lattice based cryptography.
Okay, thank you for your answer. And as I can see, it was the last one. So I would like to say thank you again. And we will move to our next speaker after a short pause. We will be back in 1 minute. Thank you. Now we are back with our next speaker. Our next speaker is Dr. Dharm Singh Jat. Professor Jat received his Master of Engineering and PhD in Computer Science and Engineering from prestigious universities in India. He is a professor of computer science at Namibia University of Science and Technology. From 1990 to 2014, he was with a College of Technology and Engineering, Maharana, Paratap University of Agriculture and Technology, Udaipur in India. He has guided about 8 PhDs and 24 masters. He is the author of more than 146 peer-reviewed articles and the author or editor of more than 16 books. His interests span the areas of multimedia communications, wireless technologies, mobile communication systems, edge roof computing, software-defined networks, network security, and Internet of Things. He has given several invited talks at various prestigious conferences. Dr. Jat, thank you for speaking to us today, and I would like to hand over the mic to you.
Thank you for a nice introduction. As you told that I am working in Namibia Institute of Science and Technology in Namibia. I would also like to share that this week our university, Namibia Institute of Science and Technology, has been awarded UNESCO Chair in Smart and Secure Environment. And I am honored to serve as chair for 4 years. And I think that platform will help to collaborate with the international community right now. So my topic is the enhanced advanced encryption standards algorithm for strong encryption and enhanced security. We know that networks are part of our everyday life in all areas today. So there is a large amount of data, both personal and private, residing on these networks, including the internet. And all defense or militaries or government organizations also connected through the network. So any loss of data from the defense network directly impact the national security. So hence these data has been protected using the strong encryption techniques, the advanced encryption standard. So, sorry. In this presentation, I will cover regarding the background, advanced encryption standards, modification of the AES, experimental design, performance metrics, and the proposed mechanism, including with the result and the conclusion. So in the background, I already told you that what is the importance of AES and AES algorithm. However, AES algorithm is known to all, and security lies only in the encryption key. AES is known to be prone to the brute force attacks of the data. So the lack of stronger and near unbreakable AES algorithm for use of defense network and other government organizations and applications remain still open problem now. There is a need to develop an or enhanced version of AES algorithm to use for the military purpose or other important government organizations or secure network, which are more stronger than the normal AES. The strength to develop a modified and stronger version of the AES algorithm to be used for military purpose by addressing the three aspects or oblique dimensions of the security. These are the high degree of randomness, high complexity, algorithm security. How to make the AES algorithm more complex, random, and hence stronger than the AES, more difficult to crack, and hence make it suitable for use of the important network or secure network like military or something else. So the presentation will cover what are the earlier modifications, what are the various techniques and methodology available, what are the effect of the proposed modification on the performance and the strength of the AES algorithm, the normal plane with the normal plane algorithm. AES is presently more secure, symmetric algorithm, and the simulation result will be slightly vary from the actual implementation because I will present some simulation results for the proposed mechanism. So the simulation result will slightly vary from the actual implementations. So these days only unbreakable cipher system is OTP, one-time pass system. So the strength of OTP lies in true randomness of encryption key. A number of attempts have been made earlier to modify the AES to make it more complex and hence less vulnerable to the brute force attacks, and also tweaks the algorithm so that even the algorithm is known to be attacker, unlike the original plain AES. However, all these modifications have not addressed the aspect of introducing near true randomness into AES, again, unbreakable. So the proposed mechanism, which will not only makes it more complex to make it less prone to the brute force attacks. It tweak the algorithm, so it is known to an attacker, but will also introduce a near true randomness in the algorithm to make it more stronger and ideal for use of defense and secure network. So the modification will be implemented in MATLAB. In the proposed modification, AES will be ideally suited for use of the secure network. Advanced encryption scheme. This is the IPS symmetric encryption standard since 2001. AES uses data block 128 bits and cipher key of 128, 192, or 256. The number of rounds for AES 126, AES 192, and AES 256, and are 10, 12, or 14 respectively the rounds. It consists of a number of transformations which are applied on the data block, iteratively a fixed number of rounds. So this is the AES encryption algorithm. Here is the AES decryption algorithm. So the encryption algorithm process of AES is shown in the left side of this figure. It consists of number of transformations which are applied on the data block, iteratively in a fixed number of rounds. So the round depends on the length of encryption key. There are 10 rounds for 128-bit key size, 2 rounds for 192-bit key size, and 14 rounds for 256-bit size. In this figure shows 10 rounds for 128-bit size. So for 10 round AES iteration, 9 rounds are similar, with 4 transformation named sub-byte. Here is something is sub-byte because letters are not visible, but the second column is the sub-byte. Shift row, mix column, add round key. So, but in the 10th round, here is this 10th round has only 3 transformation, and this mix round is missing. So there is no mix round is in the last round. AES description. The AES description process is also shown in the right figure. The description process is a total inverse of encryption process, and all transformation or iteration are applied inversely to the encryption. This is the AES byte transformation. So here is data block 128 byte arranged into 4 by 4 matrix. Initial state matrix with each element in the matrix being a byte of data. So in byte transformation, each data byte in the matrix is used as an index into the Regiondale S box. Here is, which is the 16 by 16 matrix, and is replaced with the sub-byte using 8-bit data from Regiondale S box. So this will convert the plain text matrix into the cipher matrix. The inverse sub-bytes transformation is directly inverse the sub-byte transformation, wherein each encrypted byte in the cipher matrix is replaced back with the inverse sub-byte. So the S box used is a derivative from multiplicative inverse over Galois fields 2 raised to power 8. The S box is producing by the multiplicative factors. Inverse for the given number of Galois fields 2 raised to power 8 is given with this formula. So this is the shift right. In the shift right, there is a first row is column, and second row is shift by 1 in shift right. So this is the type of circular shift, the shift row transformation. So here is the mix column transformation. In this case, this operation is substitution, but it makes the use of arithmetic same Galois field 2 raised to power 8. Here each byte of a column is replaced by a new value, which is ascertained as the sum of products of the element of one of which each of the column. All addition and multiplication operation are per Galois fields, and the inverse matrix calculated is performed similarly, but the different in the matrix. This is the key expansion. So in this case, key expansion, the 128-bit key is organized into 2D array of 4 row and 4 column. The 16 bytes organized in 4 row and 4 column. So all of 11 128-bit keys are generated. So out of 18 sets, 10 sets are used for 10 rounds for AES, and one extra key is added to the initial state of error. Generation of these keys explained with the figure. We can calculate the value of B0 by this figure. We can calculate the value of B1, B2, B3 using the formula indicated here. What are the existing work, earlier modifications in AES? Here is the hybrid cryptography using AES and hash algorithm. In this hybrid system, a message digest of 256-bit input to SHA-2. Hash functions is used as key for encryption process in AES. So the same key is later used for decryption also. The design increased the complexity of the design and hence the security AES algorithm also. So, but in this case, this increased the complexity by using hash functions, but does not address the randomness of the algorithm secrecy. Modified AES algorithm. So the basic security of AES algorithm preserved. We are not doing anything with the basic AES security. Modification ensure no fixed patterns and prove strong diffusion of and the confusion. Does not address the complexity and randomness. This one is the modified byte of AES algorithm of encryption key. Here is the 4x4. In this modification, the encryption key is organized in 4x4. Each row of matrix is then used for modification. Here using, this is the cipher key. We divided into two 4-byte here, and each byte again divided into this 00 and the 10 again in different format. And this is the format, index format for each and row and column. So the plain text is organized in 4x4 matrix. Modified shift row operations. So what we can do, we can shift, in this case, in the right shift, and this is the outcome of this one. So the first 2 bits of W and Y are given the row number to be the cyclic left shift, and the row are shifted 1 less than the number of ones X and Z respectively. Modification of fixed row column, there is a group, D and E group, C and E group, and C and E group, and D, and this is, we need a mode operations in this case. So this C is, this is the C, this is the F, this is the CF, and if this is the mode of the mode 4. And if mode 4 is 0, 1, 2, 3 is corresponding to the column. This is a column. If there is, this one is 3, mode is 3, then it's 4 column. Mode is 2, then it's 3 column. If mode is 1 and it's second column, and mode is 0, it's first column. Modify keys. So modify keys based on the hash or digest of 128-bit key calculated. Digest combined with the key of compressed to 16 bytes or 128 bytes. This 128 bits is to this 128 bits is then converted into the word. So this is and the following functions performed on the words generated the rotate word. In this case, 1 byte left shift of the input, sub-byte, substitution of each bytes using Xbox, and output is based on the XOR of the round constant and R count. Modified AES strong encryption analysis, the basic security of AES preserved, I think that we already discussed. Modification ensure no fixed pattern and provides strong diffusion and the confusion. So this is another tweaks and modified algorithm, but does not address the complexity of the randomness. So modified AES algorithm, in this case, the initial key encryption is generated using the polybice square, increase key size to 320 bits rather than the standard key of 128, 190, 256, and the ACS. So increasing the size of 220 bit rather than the standard size 128, 192, and 256 AES, increasing the number of rounds 10 to 16. In this study, this is the modified AES algorithm. In this case, it is divided into 6 by 6 matrix. The words are bifurcated in 6 by 6. So the key generation is the 6 by 6 polybasis square. The matrix consists of both numerical and the alphabet. So the plain is encrypted using the polybyte square. Each alphabet of the plain text is converted into the encryption key by using the corresponding row, first row followed by the column of the alphabet located in the matrix. Suppose, for example, the plain text is secure. Secure means S is somewhere here. S. So S means this one is the 3. Our corresponding X column is 0. So we needed 3 and 0. SE, next letter is E. E means somewhere E is here, that we have to go for 1, 1, and 4. So then the corresponding encryption key from the polybice square will be in this fashion. So increase complexity by increasing the key size and no number of rounds, but still does not address the randomness and the algorithm secrecy. Now, next study the enhanced AES by using the address. So the MAC address of machine is used as and the add of key, which in turn is used to shuffle the S box and shift row steps of the AES rounds of encryption. Enhanced AEN using the MAC. In this case, these researches that we discussed earlier propose the modification of structures in AES by using the MAC address. So the basic idea is to increase the randomness of AES algorithm. MAC address of the machine is used as add on the key, which in turn is used to shuffle the X box and shift row steps of the AES round encryption. Thus, increase the complexity and time required for the brute force attacks by increasing the total number of possibles from 2 raised to power 28, this to 2 raised to power 176. But again, does not address the randomness. This is the modification of the encryption standard. This is another study here. So this modification of AES increases the complexity by increasing the size to 384, 512, 768, and 1024 bits. So this entails the large structure and larger algebraic fields. It proposed the modification based on again Galonis fields 256 and use the data matrix 8 by 6, 8 by 8, 8 by 12, and 8 by 16 byte. So the modification version of AES is more complex and robust as compared to the original AES and the encryption decryption times of almost the same. Now the design implementation of customized encryption algorithm. So this paper proposed the customized version of AES algorithm and new protocols for safety of key exchange. The proposed new protocol for communication between two devices and options use the same protocol for multiple devices through a central server. It provides the protection against the man-in-middle attacks, which can be used to obtain the key and hence to break the cipher. So hybrid system for the central authentication and secure communication for multiple devices, but does not address the complexity, randomness, and the algorithm security. The implementation of 128 AES in MATLAB, we use the MATLAB for the implementation. For the experimental work, we measure the execution time and the maximum encryption time 87 milliseconds and decryption time of 87 milliseconds. So results superior to the similar implementation of AES. This is efficient implementation, but does not address the complexity, randomness, and the algorithm of secrecy. This is another study. AES algorithm using advanced key implementations use block size of 128 again and the plain AES, but enhanced key is 256 to 5.2 key size, and the number of rounds 10 unlike 14 plain AES for the 256 key. So improve security by increasing the key size, hence complexity, compromise the number of rounds to offset additional process time, and does not address again the randomness and the algorithm security. This one is the comparison of the parameters. AES 120, these are the parameters. AES 128, 256 bits, and the proposed AES algorithm. Key size 128, 256 looks like 512 bits. Data size blocks 128 bits. Here is proposed is also 128 bits. Round 10 to 14. Here is the 10. The time to encrypt 128 bit character message approximately 30 to 50 seconds. Here is 23 to 50 seconds. Secrecy is less as compared to the proposed AES and more than the AES 128 to 56 bits. Component that we use, the experimental is the characteristics of unbreakable encryption algorithm, degree of randomness of algorithm, complexity of AES algorithm, hybrid crypto system using the hash function MAC address, AES modification implemented in MATLAB, and the various modification of AES challenges and the result. Modification increased complexity of AES previously, increase in key size, increase number of rounds, use hash or MAC address to increase the diffusion, making it difficult to identify platform in encrypted text. So no modification truly address all these three dimensions of security, namely the complexity, randomness, and the algorithm security. So in this framework, what we use all the three dimensions, the complexity, then the higher possible combination of keys, increase resistance to brute force attacks. Again, we also tweak some the secret to include the randomness, difficult to identify all the partner. So in this proposed mechanism, we use all three dimensions and result give the better results. So the experiment framework will give the flexibility to explore the strength and efficiency of various possible modifications to the AES algorithm of fine-tune them, development of the strengthened modification of AES algorithms through three-dimension approach and implemented in MATLAB. So the experimental work is development of the suitable modification of AES algorithm which introduce the complexity and randomness into AES, implementation of simulation in the MATLAB as we already discussed, and the performance metrics that we used is the complexity 2 raised to power 28 plus 2 raised to power random number bits introduced into the AES. So this is the additional complexity that we need to measure. Then another is execution time in bit per second, number of bits of the plain text encrypted or time taken in a second for the encryption. So enhanced AES with randomized algorithm, we consider the randomness in this algorithm. So the algorithm used to introduce the randomness is based on the modern version of the Fisher-Yard shuffle for a random number generated in computers. So the function introduced the desired randomness of AES algorithm in a simple and efficient manner as to minimize the time effect on the overall implementation in AES. So the proposed enhanced AES will have nearly true random. Still, it is not true random. True random is not possible by the computer, but it is nearly true random keys which will be randomized using the algorithm. The algorithm will generate 1408-bit random number and XOR with 11 multiplied by 128-bit key required for a initial add operations and the add round key operation in each of 10 rounds of AES 128-bit algorithm. This is the proposed hence AES algorithm with randomized key. Step first here is the initialization of enhanced AES with involve the following steps. First one is the creation of the round constant array. The round constant array is an array of 32 bits words, each of which used to generate the expand key scheduled for the various round key of the key. This is in original AES. That is first 4 steps we used the original step from AES as it is. There is no change. The BIP, another part is to create a polynomial transformation matrix and inverse polynomial matrix to be used in mixed column transformation. The next one is the creation of expanded key for all rounds 11 into 128 bit from 128 bit. Create 40 by 4 bytes expanded key using the initial 16 byte cipher key, the predefined byte substitution in X box, as I already discussed in the previous slides, and the round constant to be added every 4th 16 byte subkey. Now here we modified something. This all 4 parts are the we have not there is no any change in AES, but we have something on the top of AES. So this one is the 5th one, and the 6th one part we have added additional. So in this case here is the generation of the random number matrix of size 14 by 4 done to randomize to round key matrix. The algorithm is based on the modern version of Fisher-Yard shuffles for random number generated in computers. XOR matrix are with original key matrix W to get new randomness key matrix 11 by 128 matrix, and this 128 matrix key matrix which has been randomized round key then used for initial add key and 10 rounds of encryption and decryption process we discussed earlier. So the next step is to encrypt and decrypt as per the AES transformation, but now we use the randomness S box and randomize inverse S box generated to the step, the step, all other steps. These are the results for the complexity and the algorithm. Here is the complexity of AES. We add the complexity here. Complexity of an AES randomized round keys is 2 raised to power 28 plus 2 raised to power 1408. Here we add a randomness in this algorithm. So hence the AES is the more resistance to the brute force attack, because this is 2 raised to power 128 and we have increased here is the randomness. Now randomness is 2 raised to power 128 plus 2 raised to power 1408. So hence the enhanced AES is more resistance to the brute force attack in this case, and this is on the top of the existing AES. So this is the results, the encryption timing in the terms of timing. This results is for 128 bit, 256, 12, 10248, 2048. So here, these are the results in terms of millisecond, and we can see the time we can see this one is the plain AES, and this one is the proposed AES. And we can see the time difference is negligible. Even though this is 372, this is 356, and some time is more or less or more. But time is similar, but the randomness is increased in the proposed algorithm. Now we can see with the graph here is the time. So this is the original one, and this is the proposed one. So the time is almost the same, but it increased the randomness. Decryption process is similar to the same. Here is the decryption process. In this case, in decryption process, this is 128 byte, 256 byte, 512, 1024, and this one is the original plain AES. And on the right side, we have the enhanced algorithm, and here again we see it is the same. Decryption time is almost the same as the plain AES. If we see through graphical presentations here, this one is blue one is the original AES, and the red one is the proposed AES, and the time period of decryption also the same, but randomness is increased from 2 raised to power 128 plus 2 raised to power 1408. So this is some simple example the applications deployed on the cheapest on radio and other communication system in the military applications or other applications where we need a more secure network. Implementation of routers and end devices to secure communication or defense networks, and to secure defense serverless system and the sensor networks we can also use. So where we need a more secure network than increase, because the time of execution is almost the same in encryption as well as the decryption. So the result, review of earlier modifications, AES algorithms, and an efficient modification of AES algorithms which makes it stronger through all three dimensions. So a stronger proprietary algorithm for use of military and defense network. Now the conclusion, because right now I am in time. Now the conclusion is the enhanced AES and randomness round key is a stronger version of the plain AES due to the increased randomness added in the algorithm. The strength of this modification or enhancement is that it does not change the basic mathematical structure of AES. That is important. We are not claiming anything. We have not changed the original mathematical structure of AES. Only we add the randomness as additional security of the element. So the comparison proved that the execution time for both encryption and the decryption for both plain AES and AES with randomized round key are comparable. The only additional time taken in the proposed AES is for the randomness number generation and the XOR operation with the 11 into 128 bit round keys, and this taken a total fixed time of only 20 milliseconds, which is only a one-time operation, and it is not affected by the data size to be encrypted or decrypted using AES. So hence, we are able to achieve much higher security, but with negligible overhead charges with the existing AES. These are some references that we used in the study. Thank you. Now floor is open for the questions. Thank you.
Thank you, Jet, for your presentation. We have several questions here. I will start with the motivation. Please, could you share your reasons for believing that AES is not strong enough So it's about motivations to re-implement the AES.
Yeah, so I shared the study in, I think, in my slides, that there was a study that the existing AES is attacked by brute force based on the study. I mentioned in the slides presentations.
And could you briefly repeat your motivation?
You see, there is no 100% secure networks right now. Nothing is 100% secure. So I can say there is no lock without key. And there are so many modifications that I included in my presentations, and one of the presentations included about the AES present AES algorithm is also affected the brute force thing.
Okay. The next question is related to analysis of your novel design. Who analyzed your AES modification, and it's confirmed that you introduced no new weaknesses into it?
Say again? No, you see, in the proposed mechanism, we added randomness. So randomness increase the number of more round randomness now hackers cannot. They're difficult to. You see, there is no in the computer system. We don't have a truly random generator, but we can go towards the truly random generator. So in this case, we increase the randomness, and we generated. We try to develop a truly random generator, randomness to increase the complexity.
And was your method independently reviewed or not yet?
Say again?
If your method was independently reviewed or it was not yet reviewed?
No, it was published in IEEE Explore. I mentioned in this in one of the presentations. The reference is also there.
Okay. I will try to obtain next question. In the chart shown, was any explanation found for some having less time in processing the key than original AES? For your AES with random round.
So I shown in one of the flow chart that 4 steps are used in the original AES. We have not changed the mathematical structure of the AES, but we have added some additional security. So we increase the randomness and add on this one.
Okay.
But mathematically, still AES is the strongest key right now these days in every part of the world. But what we did, we have not changed any mathematical structure in AES, and we added on the top of that AES.
Okay. Then the question related to pseudo-random number generator. What do you seed your pseudo-random number generator with?
Yes. No, we used, you see, in the pseudo-random, we used the initially pseudo-random generator based on the existing. Here is somewhere. I need to go back. Sorry.
Okay.
Yeah.
Did you consider impact of your modification on hardware implementations? For example, hardware accelerators?
Yeah, we developed a MATLAB, then we can implement in hardware. That's why in the last slides, the application we read, I already mentioned. So because you see right now, what is the problem in military, especially in military? People, OTP people, they are transporting physically from one place to another place. And every time once OPT used, they cannot use that second time. So what we tried to increase the complexity only. It's not 100% secure, but we try to increase the complexity. And we can implement it in hardware. Yeah.
It looks that we have some small technical issue. Can you hear us?
Yeah, I can hear you.
Okay.
So you see, it's not tested on hardware because these results based on the MATLAB. And there may be the slightly difference between the actual implementation and the hardware implementation. Maybe some results can be changed, some percentage.
Okay. Thank you very much, Jet, for your answers. I would like to thank also our audience. Thank you for joining us. As we are on the time, so we can conclude our session. And I would like to remind you that our conference is not over. We will continue with 2 sessions. It will be dealing with cyber attack at 2 p.m. US Eastern Time, which is 6 p.m. UTC. And the last session will be access control in a touchless society in 6 p.m. US Eastern Time, which is 10 p.m. UTC. If you are interested in the next sessions, please visit our website. It's https tc.computer.org/dvp-conference. There you will find any details. We will looking to see you during our next sessions.